This is a continuation of section 7.4 on partial fractions. So within the last lesson, we looked at some steps on going through a decomposition of an expression that's a fraction, a rational expression. So the first part said that in order to go through the decomposition or break the fraction apart, we want to make sure the numerator, the degree of the numerator is one less than the degree of the denominator. If it isn't, we use long division, and we went through a couple examples like that. Item 2 says we want to factor the denominator. So if our degree of the numerator is one less than our denominator, we proceed to step 2 here. We factor the denominator as much as possible. And all denominators factor into products of irreducible linear or possibly quadratic factors. So parts A and B, we looked at linear factors, none that repeated, and then some that did repeat. Part C here, we're going to look at irreducible quadratic factors where none are repeated. So we're going to practice this example. We're going to go ahead and decompose. The fraction 5 over x times a quantity x squared plus 1. So our first factor is linear, our second factor is quadratic. So I could separate this into a over x. And now when my denominator is quadratic, I want my numerator to be linear. So I need a bx plus c. That would be a linear expression over x squared plus 1. And then I go through the same process. So a is going to get multiplied by the x squared plus 1. But now bx plus c, because it's a binomial, I need it in parentheses times x, well, this needs to equal the 5. So now I just pick different values for x. How about with this x here, let's let x equal 0. So 0 squared plus 1 is just 1, so I'll have a 1a or 1. This will turn the whole second term just into 0, so a equals 5. Next, let's let x equal 1. So this is 1 squared plus 1, so I'm going to get a 2a. Over here, this will just give me a 1b plus 1c is going to equal 5. Now, unfortunately, I have two unknowns here still, but that's okay. We'll do this once more. 2 times a is 2 times 5, so that's 10 plus b plus c equals 5. So b plus c equals negative 5. Now let's let x equal negative 1. So this will still turn into 2a. Now imagine the negative 1 here and here. So that's a negative 1 times a negative b, so that turns into a plus b. Negative 1 times c is a minus c, and that still equals 5. Again, 2 times a is 2 times 5, so I get 10 plus b minus c equals 5. And now b minus c is going to equal negative 5. So we're using all this wonderful algebra. It's coming back in all of these steps here. So now I have a system of equations. I can join these together to say b plus c equals 5, and then b minus c equals negative 5 for both. So now the c's cancel out, and I get 2b is equal to negative 10. So b is equal to negative 5. And then this will allow me to solve for c. So if b plus c is negative 5 and b is negative 5, c is 0. So I found my values for a, b, and c. So now, if I actually wrote this as an integral, so now I could say, if I wanted to evaluate the integral of 5 over x times a quantity x squared plus 1 dx, I can decompose this fraction, so it's the integral of, remember, it is a over x, so that's 5 over x, plus the integral, b is negative 5 and c is 0, so I'll get a negative 5x over x squared plus 1. Now this will be a lot easier to take the antiderivatives of. So the first part here is just going to become 5 times the natural log of the absolute value of x. And I could actually just say minus. I'm going to move the 5 out in front. And then I actually want to use, so if I write this as x over x squared plus 1, I actually do need to use u substitution here. It'll make this a lot easier. So let's let u equal x squared plus 1. du is going to equal 2x dx. So x dx is going to equal du over 2. So now this becomes 5 times the natural log of the absolute value of x. I'm going to move the 1/2 out here with the 5, so we'll get minus 5 halves times the integral 1 over u du. So now this is 5 times the natural log of the absolute value of x minus 5 halves times the natural log of the absolute value of u, but we could go ahead and put this back in, x squared plus 1, and then plus c. Right, and then the final case here is that we have irreducible quadratic factors. Some are repeated. So let's go ahead and decompose this fraction. And that's all we're going to do. We're just going to get to the sort of the first step of this. You're going to come to find out some of these can get very complicated very quickly. So I'm just going to rewrite this. Now remember, we have to build up to larger powers here. So I'm first going to start with a over x. Then I need b over, actually bx plus c, because this has to be over x squared plus 4, and that denominator is quadratic, so I need a linear expression in my numerator. Then I'm going to have the x squared plus 4 quantity squared, so this is still quadratic inside the parentheses, so I'm going to have a dx plus e. We have another linear. Then finally I'm going to have the quantity x squared plus 4 cubed, and then we could say fx plus g. And that's all the further we're going to go with this one. So in our next example, again, I want to just kind of go back over this first step. We're going to write out a PFD, a partial fraction decomposed for this fraction. This looks fun, doesn't it? Again, we're just going to go through the first step. So I'm going to start right here. So I want you to just notice each factor. That's what our focus is on. Anything that has a larger power than 1, we have to build up to. Now for this first one, we're just going to start with a over x, but we have to get up to x to the 4th. So all of these denominators are still going to start with a linear factor, but to a different power, so I still keep a constant. So then we're going to have plus b over x squared plus c over x cubed, and then plus d over x to the 4th. Next, I still have a linear, x plus 1, so I just need another constant e. Next, I have to build up to the x plus 2, that quantity squared, so it's still linear, so I can just have f. And then I need that squared, but it's still a linear that's squared, so I could just say g. Next, I have an x squared plus 1. That's quadratic, so I need an hx plus I. Then I still have a quadratic. I'm going to write this out before squaring it, so I just write it out to the first. Again, because this is a quadratic, I need a jx plus k, and I ran out of room, so I'm just going to continue this down here. So I still write this, but now I'm going to square the trinomial. And I still need another linear, so we could say lx plus m. All right, if you wanted to try this, you probably just need quite a few sheets of paper here, but we're not going to. Like I said, I just wanted to show you an example, again, just stressing how we build up to the larger powers here. All right, so let's try an example, nothing near this length here. Let's just go to another example where we're jumping right into the integrals here. So let's go ahead and integrate. So I first just want to take the fraction and work with this. We want to decompose this fraction. If you want to pause the video and give this a try, you can. So if I look at my first factor, that's linear, so I'm good with just saying a over x minus 1. But my second factor in my denominator is quadratic, so I need a bx plus c over x squared plus 9. Luckily, nothing is to larger power, so we didn't have to build up to anything. So just like before, I continue here. I'm going to multiply a times the quantity x squared plus 9. Plus, we need parentheses here, bx plus c times the quantity x minus 1. Well, that's going to equal 10. So I'm going to start, let's start with x equals 1 here. And I chose that because that will go to 0, which will make this whole term go to 0. So this will give me a 10a equals 10. Therefore, a is going to equal 1. Next, let's go to an x equals, let's do 0. So this will now give me a 9a. And if x is 0, b goes away, but this becomes a negative 1c, so then we get a minus c is going to equal 10. Now we already know what a is. A is 1, so we get a 9 minus c equals 10. Negative c is going to equal 1, so c is going to equal negative 1. Now maybe let's choose x to equal a negative 1. So now this gives us, this will still give us a negative 1 squared is 1, so we'll still get a 10a. Now very carefully here, we have to do negative 1 minus 1, so that's a negative 2, and then we get a negative 1b. So negative 2 times negative b becomes a plus 2b, and then we get a negative 2c, and then that's going to equal 10. So again, a is 1, so we get a 10 plus 2b. C is negative 1, so this gives us a plus 2 equals 10. 10's cancel out. We get a 2b is going to equal a negative 2, so b is equal to negative 1. So now we continue this. So now our integral of 10 over the quantity x minus 1 times the quantity x squared plus 9 becomes the integral of a over x minus 1. So I'm going right back up to what's in purple here. A is 1, so we get a 1 over x minus 1 plus bx plus c. So that's going to be a negative x minus 1 over x squared plus 9. So negative x minus 1 over x squared plus 9 dx. So this is definitely a lot simpler than what we started off with. The first one, much easier. Now we could just say it's the natural log of the absolute value of x minus 1. Here I'm going to say minus, I'm factor out a negative from right here. Actually, what we could do is separate this. So we could say minus the integral of x over x squared plus 9 dx, and then minus the integral of 1 over x squared plus 9 dx. So I just separated this. So this became a negative x over x squared plus 9 minus 1 over x squared plus 9. And we have to do a little bit of work with each one. So under this next one, just like in our last previous example that we completed in full, I'm going to let u equal x squared plus 9. And then du is going to equal 2x dx. So that du over 2 is going to equal x dx. And then what I could do over here is I could rewrite this. Let's actually start by factoring out a 9. So then this becomes 1 over 9 times x squared over 9 plus 1. And then I could look at this as 1 over 9 times the quantity x over 3 squared plus 1. And I'll come back to that. So right now we have the natural log of the absolute value of x minus 1 minus, we could say 1/2 of 1 over u, the integral of 1 over u, and then du, because that's our x dx. And then I could write this as minus 1/9, take the 1/9 out, and then the integral of 1 over x over 3 squared plus 1. Still leave this as dx. There's still a little bit more we have to do right here. All right, but our next step, natural log of the absolute value of x minus 1 minus, we can say it's 1/2 times the natural log of u, but we just said u was x squared plus 9. And then here, I'm going to go a little bit further and let u equal x over 3, and then du is going to equal 1/3 dx, so that 3 du is equal to dx. So now this becomes, I could say 3/9 times the integral of 1 over u squared plus 1 du. I want you to take a look at that last term, see what you think that's going to be. You could leave this as 3/9, or you could say it's 1/3. But this is an inverse trig function here. It's actually the inverse tangent or arctangent of x over 3, and then we could finally put that plus c. So quite a bit for one problem. All right, and then the last type we're going to look at, it's a little different. It's called rationalizing substitutions. And we do this if the integrand, the stuff that's underneath or within the integral, contains a root. So we could say it's the nth root of some function g of x. What we end up doing is we substitute u is equal to this nth root of g of x. So a nice example here. Let's go ahead and find the integral of 1 over x minus the square root of x plus 2 dx. So we're going to start by letting u equal the square root of x plus 2. We're letting u equal the root part of this. Now here's the trick. We're not going to find du. We're actually going to square both sides. So u squared is going to equal x plus 2. Then this allows us to say that x is equal to u squared plus 2 minus 2. Then we could say dx is going to equal 2u du. So now the integral of 1 over x minus the square root of x plus 2 dx becomes the integral. We could just write 2u du up top, or 2u, we could put the du off to the side, over, so we know x is equal to u squared minus 2, and then minus this whole part right here was just u. Now I could put the 2 outside, and then we get u over. Now what we could do, I'm just going to rewrite this as u squared minus u minus 2. Now we can factor our denominator, and it takes us back to what our previous problems were. So we have u over, this will factor into a u minus 2 and a u plus 1 du. And now we can use partial fractions. So let's let u over the product of these two binomials become a over u minus 2. They're both linear, which is nice, plus b over u plus 1. Again, if you want to pause the video to continue here, see what you come up with. If not, you could just let this play. So that means a times the quantity u plus 1 plus b times the quantity u minus 2 has to equal u. How about we let u equal 2 first? That means b will just turn into 0. This whole second term becomes 0. So we're going to get a 3a is equal to 2, because u is 2. And then a would equal 2/3. Then we can let u equal negative 1. Now the a term will go away, and we'll get a negative 3b is equal to negative 1. So b is going to equal 1/3. All right, so now we'll say 2 times our integral of u over the quantity u minus 2 times u plus 1 du becomes 2 times the integral of a over u minus 2, so we'll have 2/3 over u minus 2, plus b, which is 1/3 over u plus 1 du. So now this becomes 2. We just leave the 2/3 here, because we know this will become the natural log. It's like 2/3 times 1 over u minus 2. So we get this plus 1/3 times the natural log of the absolute value of u plus 1 plus c. But we want to get all of this back in terms of x. So we just go back up here to x, or rather u is equal to the square root of x plus 2, and we'll replace that. So now we get 2 times the quantity 2/3 times the natural log of the square root of x plus 2 minus 2 plus 1/3 times the natural log of the absolute value of the square root of x plus 2 plus 1 plus c. Okay, so we'll stop there for this section. When I go to start section 7-8 next week, I'll start by reviewing a couple problems from 7-4 here. But as always, take care. Let me know if you guys have any questions over either video for this section.